Hi everyone, we are Aydın Aksoy and Mustafa Feyzioğlu, and this is our graduation project. It is about classifying EEG signals using support vector machines. So what is an EEG? EEG is an electrophysiological monitoring method to record electrical activity of the brain. It is done by placing electrodes along the scalp of the subject and reading the electrical differences in voltages usually, and they are recorded in patterns. They are more commonly known as brain waves. But there is a slight problem in this method, because there are no standard methods to interpret results. Technicians and doctors need to go through the footwork before the actual diagnosis of the signals, and because of this, a machine learning approach is suitable here. Thus, we examine datasets and algorithms and implement and work on a specific dataset to demonstrate the idea. Our dataset consists of 20 individuals in both training and test sets. They have 10 control and 10 alcoholic individuals. They have 64 channels. The channels correspond to the electrodes placed along the scalp. And we sample the data at 256 samples per second. That means we are using a sample of 256 Hz in frequency. And there are three stimuli in the dataset. They are denoted as S1, S2, and S3, and there are 10 trials for every stimulus. You can see example plots over here, an example plot of the healthy individuals on the left and an example plot for the alcoholic individuals on the right. So our methods are like this. We read the data first, of course, and we try to classify the data using the libSVM library. First we only use the training data and change the parameters of the SVM train method from the libSVM library, and then we try to select several subsets to optimize the model we train, and then we use the PCA, that stands for principal component analysis and normalization. But these two methods yield no significant results in our case, so we decided to omit them. And then we try to select features using a Feast toolbox on MATLAB, and we average over the trials. That is, we average over the 10 trials for each individual. So it's like every individual has one trial in the end. And lastly, we train ELMs. They stand for Extreme Learning Machines. To compare the results, we train them with and without cross-validation. So let's go on with the code and show you how it's working. This is our file reading method, but we won't go into so much detail about this because we have saved the whole dataset that we're going to use in a MAT file named data.mat. Let's clear the workspace first so that we can see the results better. We can evaluate this section to load up the data. As you can see, there is 5-dimensional matrices consisting of training and test data. Here we can see an example plot of an individual's data. For example, if we select the third person and take the third stimulus and average over the data over 10 trials, we can show the results. Let's evaluate it and take a look. So this is the average data for third individual in our training set. Over here we can sample the data and select subsets. For example, I can only take the first stimulus into consideration when training the model, or I can take 1 and 2, or I can take 1 to 3, and I can select the number of trials that I want to use to train the model. Usually the best accuracy is achieved when we take into consideration the whole stimulus, that is from 1 to 3, and whole trials. And then we concatenate the training and test sets to select the features from later. In this section, as we mentioned before, we average over the data of 10 trials so that every individual has one trial. Let's evaluate this section as well to see the results in the following section. And here we train the libSVM method. Let's see. We forgot to evaluate this section. Yes, okay. So let's evaluate this section. As we can see, use the averaged data set over here, and it gave us the 95% accuracy, and this is the best accuracy we achieved in our project with optimization. Actually, let's go on and evaluate this section as well to compare the model without optimization. This is one of the main reasons we didn't use the whole dataset from the website. We only used the large dataset because of time concerns. As you can see, the accuracy is 79.5. It is less than the optimized version. And here we use the feature selection. We are using the feast toolbox, and we are using the relief parameter because we figured that it works the best and most efficiently. Let's evaluate the section to see the results. This will take a while because again we have so much data, we didn't want to use the whole dataset because of this, and the other parameters take much longer in feast toolbox. After the results arrive, we take a histogram and show which channels or electrodes represent the data best. As we can see, the histogram is displayed over here, and let's have a look which electrodes are representing data best. So 10th, 14th, 15th, 17th, as you can see, the list goes on. These electrodes or these channels represent data best, and we try to use them in training our models, but as you can see, they are not very efficient in classifying the data. Averaging over data is still the best option. And lastly, we train our ELMs, extreme learning machines, and we use a cost value of 10 over minus 5 to 10 over 5, and we are using 10, 20, 50, 100, 200 and 500 neurons. As you will see soon, we will get the best result in 10 over minus 4 cost value, and as you can guess, the accuracy increases as the number of neurons increase. This will take some time, as I said. Yes, the results have come, and yes, as we can see, this is the best accuracy around the cost value of the 10 over minus 3 and 500 neurons. So this concludes our project video, and thank you for watching. See you later.